This is the video on Introduction to Chemistry. Chemistry is something that we have to talk about in biology because the reactions in our body are dictated by tiny little charges that happens in chemistry. It affects things like how DNA opens and closes, how medications work in our body, and even just how simple things like our muscles move and how our brain stores information. It's all basically chemistry. So we are a huge chemical reaction. So one of the things that I wanted to stress with you is that what something looks like really does determine its function. So like a screwdriver, if you think about the head of a screwdriver being flat at one end, the structure of it really does determine its function and what it does and how it works. Well, that's the same for chemistry, and you're going to see that's a very big theme in biology from the start all the way to the end. So before we get started with chemistry, you kind of have to know the big picture. And if we start to talk about chemistry, we kind of break things up into things like matter. Matter is something that takes stuff up. It has mass. So mass means it just takes up some space. An element is a basic unit of matter that is visible without like really breaking it down into like small atoms and things like that. So when we think about elements, you might think about the periodic table of elements, and that's basically where matter could be a ton of these chemicals put together, but when we break that down to the simplest components, elements, they're just one piece or another piece. Another way to think about this is if you think about Lego, if you're building like this huge ship, it might be, tons of pieces of parts. But if you were to break those parts down to the smallest component, that would be an individual Lego block. And that would be like the equivalent of an element. You could put those elements together and build something huge, or you can rip them apart and rebuild them. And that's going to be a theme that you're going to see in pretty much this whole semester. The periodic table has about 116 elements. Some of them only last for microseconds, but some of them will last forever. We're going to really only discuss a couple of them because there's about 25 elements that are in humans, and those are the ones that we really focus in on. But the most common, and this typically ends up on exams, what are the most common elements in humans? They're going to be oxygen, carbon, hydrogen, and nitrogen. Nitrogen is used in our genetic structure. Hydrogen is used in water, and so is oxygen. We're mostly made of water. Carbon as well is pretty much the building block of us. We're mostly carbon because our bones are made of carbon, muscles. Trace elements are things that we don't need a ton of, but we just need a very little amount, like something like copper. Copper, we don't need a ton of copper, but we need a small amount to keep us going, and we'll explain that later when we get to enzymes. An atom is the smallest unit of an element, and it's made up of 3 subatomic particles. And you've probably heard of these before, so I'm going to go kind of quick. A proton, a neutron, and an electron. A proton sounds like positive, and it's a positive charge. A neutron sounds like neutral, and it's zero charge. An electron, this is the only one you kind of have to remember because the name doesn't help you. Electron is negative. I guess you could think of electricity as having some sort of static sort of to it, so that's negative. If we look at the elements above, you could see that the protons and the neutrons, they hang out in the middle of the element, and that area is called the nucleus. It's not the same nucleus that we're going to talk about in a cell, but that's kind of where we got that term from. Electrons, you could see on the outside of that element, right over here, you can see that they float around the outside, almost like orbits, like how the Earth would be in the middle and the moon would sort of orbit around it. They're the same exact way. This is probably a better representation of them because they don't really have this perfect little ellipse that they do. They sort of wiggle around the outside, but they're always outside the protons and neutrons. If we continue with some terms, the atomic number is the number of protons. So if something has 2 protons, 2 electrons, and 2 neutrons, it'll say what's the proton number, and that's would be the atomic number. Determines the identity of the element, and that's kind of how we place things on that periodic table. So for instance, here we have He, and that 2 represents the number of protons. The mass number is the number of protons plus neutrons. So for instance here we have 2 protons, and anytime we have typically 2 protons, we're going to have 2 neutrons and 2 electrons. Unless it's becoming a molecule, then it might share some things, but this thing's on its own. So protons plus neutrons, that's 2 plus 2, and that's going to equal 4, and that's why that 4 is at the top. Atomic number and mass number, those are terms that get mixed up pretty easy. Just think mass means more than one thing, so that's protons and neutrons, and atomic number is really just really referring to protons. If you remember that, you should be okay. And again, the atomic number is going to be just the protons, the mass number is protons plus neutrons, and remember that protons and neutrons live inside the nucleus, and the electrons do float on the outside. We do have some things that are a little different, and I wanted to bring this up because when you give patients medications, you're going to give them this thing called an isotope, or something that's radioactive, so we can track it in their body because it looks so different. So it's the same element, but a different mass number. So the same number of protons, but different number of neutrons. So for instance, if we look here at carbon, the first one, carbon-12, because it's got 6 protons and 6 neutrons, we call it carbon-12, or that's normal carbon. Carbon-13 is 6 protons plus 7 neutrons, so you can see it's got an extra neutron. That also means it's slightly radioactive. But then if we go to carbon-14, you can see it's got 2 extra neutrons, so it's got 6 protons, 8 neutrons, and the electrons are 6. But this, it should be ideally 666, all the same number, but you can see this one has 2 extra neutrons, and that is going to give it that radioactive property. And we can actually track this. So if you've ever heard of people going to the doctor and having this radiation therapy, or they drink something and we could see how their GI tract is working, well, they're drinking a really weak isotope, and we can actually track that with certain medications to see what's going on with their small intestines and large intestines and things like that. And then I am going to cover this one in my next video.